Okay. Hi, my name is Yik, and I'll be talking about our work on performing safe human-to-robot handovers of unknown containers. So performing human-to-robot handovers of unknown containers in the real world is challenging and potentially unsafe. And the robot may pinch or strike the human accidentally if the estimation of the human's hand pose is inaccurate. Or fragile containers may break or deform, and if the containers have fillings, they might spill if incorrect forces are applied, which can cause harm to both the robot and the human. So physics-based simulators can be used to ensure the safety of the interaction when developing robot control algorithms for handovers. And there are some existing works on simulators for handovers, and they mainly focus on the visualization of the handover trajectory, or they are limited by the use of primitive shape objects like cubes or spheres. And they're also limited to setups where the robot stays stationary and the human placed objects in the scripper. So here we propose a modular real-time simulation framework for developing and evaluating algorithms for safe human-to-robot handovers. And we address these limitations by simulating the contact forces during the handover. And we reconstruct the handover objects with a fission-based method. And we consider fully dynamic setups where both the robot and the human approach the handover location together. So we start from RGB videos of human pouring fillings into containers and handing them towards the robot. And the videos start from the object manipulation phase, where the human prepares the container for the handover by pouring fillings such as rice, pasta, or water into the container up to various fullness. Then the human hands the container towards the robot in the human maneuvering phase, as if to perform a handover. So we perform perceptual estimations using our fission-based pipeline to estimate the physical properties of the container, such as shape and the trajectory. And we recreate the handover in the simulation environment. So in the object manipulation and human maneuvering phase, the container will follow the trajectory estimated from the real video. Oh. Sorry, the video wasn't playing. Yep. So the object will follow the trajectory estimated. And after it's playing. So the robot will attempt to grasp the object by estimating a safe grasping area on the object and attempt to deliver it to a target delivery area behind the robot itself. So here's overview of our simulation environment. We have a reconstructed container, and we have a fixed hand model with the pose estimated by our fission pipeline. We have a safe grasping region estimated to be grasped by the robot. And we have a UL5 robotic arm and a robotic 85 gripper to perform the handover in the simulation. And we have a target delivery area behind the robot. So in a perception pipeline, we first estimate the object shape using an iterative shape fitting method based on the cementation mask extracted in the first frame of the video. We also perform hand key points estimation to retrieve the hand pose and the joint angles of each finger. And we perform object cementation, and we obtain the centroid location as the container location in each frame. And we use the hand pose of the hand that is holding the container and apply that as the container pose in the simulation. As annotation, we also obtain the object mass using an electronic scale. So in order for the robot to safely grasp the container and an area that is not occluded by the human. We first extract hand key points that are close to the container, and we predict a unsafe region based on the relative height of the container. And we initialize a safe region based on the estimated dimensions of the container. And we subtract these two regions to obtain the final safe region for grasping. So the robot should grasp at this location to avoid harming the human. We also perform filling mass estimation for the transparent containers so that the robot can have an idea of how heavy the objects are. So we train a CNN based on bounding box of the object cropped from a cementation mask. So we combine that with the annotated container mass to obtain the object mass. And we use a previously learned linear model to predict the grasping force required to hold and deliver the object. And other modalities such as audio can be used for containers that are opaque. So we model the human safety in terms of the distance between the robot and the robot's gripper and the human's hand. If the human is too close to the robot, we assign a low human safety, and otherwise the handover should be safe for the human. We also model the object safety in terms of the predicted force to be applied by the robot on the object, and also the minimum amount of force required to hold and deliver the object. So if excessive force is applied, the object may deform and filling might be spilled. And if insufficient forces are applied, then the object can fall. Otherwise, the object is considered to be safe during the handover. So here we showcase some example results of the simulated handover. With our safe grasping region estimation, the robot grasps the unoccluded region on the container successfully for the handover. And without safe grasping, the robot will pinch the human hand while trying to grasp the object at its centroid. And if there is not enough area on the container to be grasped, the robot will stay at a distance to avoid harming the human. And here are more examples of the simulated handovers. So here we have containers with different shapes. And even if the safe area is estimated, if the force is not enough, the object will fall and the filling will be spilled. And here is another example where the delivery angle is not optimal, so the container will fall based on its narrow shape. And here we finally have a successful handover and the delivery. So in summary, we propose a novel modular real-time simulation framework for human-to-robot handovers. And this allows the simulation of handovers when the robot is not accessible. And we estimate the properties of the objects manipulated by a person without the use of markers, motion captures, and scan 3D models. And we also provide a baseline for estimating safe grasping region for a handover. And we quantify the handover safeness for both the human and the object. And future work will include validation on a real robot and to improve the simulation with deformable objects and content dynamics. And thank you for listening.
Yeah, thank you very much,